Hey folks, this is the second video in section 8.7. We're going to be graphing some polar equations. Notice that I have the graphing calculator out here. This is the TI 8384. So you might want to go ahead and pause the video and pull your calculator out. We are going to be working with it during the next few questions. So go down, please, to example number 3. And we won't be using the calculator yet. So let's just take a look and see what the instructions say. For each rectangular equation, you say, well, how do you know it's rectangular? Well, remember, rectangulars have x's and y's. So this is definitely a rectangular equation. The first thing that we're asked to do is to change it to a polar equation. And then after that, we can sketch the graph. All right, so changing to a polar equation. I have x's and y's. I want r's and thetas. And you remember we had a box up here that gave us some equations that we can regularly use for this. So all 4 of these equations are legitimate when we want to switch from one type of equation to another type. All right, so first thing let's go ahead and do is y is equal to r sine theta, x is equal to r cosine theta. Let's go ahead and just simply substitute those equations for x and y. And at this point then, when it says to give a polar equation, in my lab, in the courseware, you're going to be expected to isolate r when you do this. And it'll actually make sense why in just a bit, but you are expected to isolate r. So let's go ahead and move the 2r cosine theta over to the left-hand side. And then we can factor out a GCF of r. And then since we're trying to isolate r, let's divide on both sides by this parentheses. And this is what we have. And when you look at the second thing that you're being asked to do to sketch the graph, I would ask you, would you rather sketch the rectangular or would you rather sketch the polar? And obviously, the rectangular would be easier here. We understand that this is y equals mx plus b form. This is just going to be a line, where -4 is the y-intercept and 2 over 1 is our rise over run, or our slope. So that's what we will do next. Notice that I've already actually gotten the -4 marked on the graph. And then if I'm rising 2 and running to the right 1, basically what we're looking at here is rising 2, running to the right 1, rising 2 more, running to the right 1. So this right here is going to be 2 coordinates that I can connect. And then that is my line. All right, for the second question, again, the first instruction is to change into a polar equation. Well, x squared plus y squared is the same thing as r squared. So let's replace x squared plus y squared with an r squared. And all of a sudden then, when I take the square root of both sides, my r technically is either a plus or a -5. But as we learned in the last video, radius of negative is not as normal. We can work with it, but either way, we're going to have the exact same thing here. A radius of 5 tells us that we have a circle with a radius of 5. Now, I can cheat here a little bit because my iPad will automatically draw a circle for me. All right, so now let's go to example 4, where we are graphing something like this right here. Our instructions actually tell us it's a cardioid. We'll take a look at why that is in a little bit. And here's where we're going to be using the calculator. Before we use our calculator, though, there's a couple of things that you need to mess with. All right, so if you would please go to the mode button on your calculator, the mode button. Couple things. Make sure that number 1, you're in radians. Secondly, notice on my screen, it's the fourth line down. Notice that I have polar chosen. Okay. Those are going to be the two main things that you want. The second thing that you want to look at is the window. The window, and notice that the window is different than what you're used to. Now it has this theta min and max as well as a theta step. So my theta min and max is going from 0 to 2 pi. Notice that 6.28 is the same thing as 2 pi. So in other words, my thetas are covering one whole entire unit circle from 0 to 2 pi. My theta step, yours may or may not be the same thing. In fact, I was kind of playing with this a little while ago, but common theta steps are either going to be pi over 12 or pi over 24. So let's say I do pi over 24. I would actually type in pi divided by 24, and I would get this decimal right here. At the moment, notice that my x min and max and my y min and max, these are just my standard windows here of -10 to 10. So domain and range both of -10 to 10. Okay, so once your window is good and your mode is good, let's go into the y equals button. And you'll notice that now it doesn't say y equals like it used to. It says r equals. Now I've already typed it in, and we're only looking at example 4, so that's going to be the very first one, my R1, and which, by the way, see how it says R equals. That's why in the last two questions I mentioned that my lab will expect you to isolate R, and that's one of the main reasons. So we have r is equal to 1 minus sine theta. You say, well, where's the theta button? Think about where your old x button was, and that is where your theta button is. So same place there. Now, we can go ahead and graph. So once you get that typed in, or your R1, once you have that typed in, we can graph. And you're probably going to notice that it's a little bit hard to see. All right. Now, couple things. First thing is that we want to mess with our window. All right. So notice that all of my graph is basically looks like from -3 to +3, both on the x's and the y's. So go into your window, leave your thetas alone, but go from -3 to +3. For the x min and max, and might as well for the y min and max as well. And then you can go back to the graph. But one thing that you notice is that it still isn't quite, it doesn't quite look right. And the reason is because the left and right units should be the same as the up and down units, because our domain and range is from -3 to 3. However, we're looking at a rectangular screen, and so the left and right units are longer than the up and down units. Now, my digital calculator, I cannot fix this, but you can. So let me show you how, but I have to do this another way. So if you go to the zoom and go to number 5, zoom square will actually cause your horizontal and vertical units to be exactly the same. Nothing changes when I do mine. However, I can stretch mine out a little bit. And now I have more horizontal and vertical matching. So this is a cardioid. And you say, well, how do I draw this on paper? All right, so what we're going to do is you're going to go to trace, just plain old trace, up here on the top corner. And a lot of times, now mine didn't do this, and for the record, sometimes this digital version doesn't work. It is fairly new, and so they're still getting some kinks worked out. But yours should have landed, I don't think I can even point to it. I don't think it'll show it. It should have landed on the positive x-axis. And so, let me see if I can, yeah, I can't even, yeah, it won't really let me mess with it a lot. So, let me see if I can do it manually here. Try to be patient as we wait. Sorry, wish this was going faster. Okay, more than likely, this is where yours was. Maybe somewhere close to here is what I'm guessing. That's usually what it is. So this ends up being at the coordinate 1, 0. So over on my graph, I'm going to mark the coordinate 1, 0. Using my trace function, this is going to feel a little weird, but you're going to go to the right. I know it feels weird, but when you go to the right, you're going to follow the curve in a counterclockwise fashion. The next important coordinate is going to be at 0, 0. Again, on your calculator, I'm guessing it'll hit right at 0, 0. Mine's just not being cooperative right now. Keep on going around. And you'll probably hit the coordinate negative 1, 0. And then if we keep going to the bottom so we can get our y-axis, I can't really get too close to it, but I'm going to guess it's around 0, negative 2. So once I have my x and my y intercepts marked, then all I have to do is fill in with the general shape of that cardioid. Doesn't have to be gorgeous, but that's what we're looking for. All right, example number 5 is r equals 4 cosine 3 theta. So let's go back to your y equals. I've already got mine marked in here. Just make sure that your parentheses are in the right spot. And if I go straight to graph, you'll notice for mine, this is way off the page. So if we go back to zoom in the middle and go to number 6, zoom standard, this will take us back to that negative 10 to 10 domain and range. And what we have here is it's called a 3-leaved rose. It's a rose that has 3 leaves. Now, if you want to zoom in a little bit, you could change your window to maybe -5 to +5 for both x's and y's. That would be a good window. And then you would also want to square it up as well. Again, by using that zoom button in the middle, zoom 5 is where you can make your horizontal and vertical units matching. All right, if we use the trace function, again, let's see here. You probably will hit the coordinate 4, 0. So I'm going to go ahead and put that on my graph over here. And basically what happens is when you have a rose, the leaves are all going to go out the same distance. So all of my leaves then are going to stretch out to ring 4. So all 3 of them. Now, the other thing that you can realize is that think about the fact that these 3 leaves, how do I say it? If you go all the way around the circle, that's 360 degrees. If you divide 360 degrees up in 3 equal ways, then each one of those leaves is going to occur every 120 degrees. Okay, so my first rose occurs here symmetric to the positive x-axis. My second rose is gonna, the tip of it is gonna be on the 4th ring, and it's gonna be through that 120 degree spoke. And then if you go another 120 degrees, my 3rd leaf is gonna be at the 240 degree mark, again, going out to ring 4. So then that would be an example of your 3-leaved rose. Couple of interesting things here. that we can point out. These two are our rows equations, and just a few little interesting things. You can kind of play around in your calculator with these. All right, example number 8, converting a polar equation to a rectangular equation. A few minutes ago, we went the other direction. And so we were asked to write an equivalent equation, and then we were also asked to graph. And at this point, I'm actually finished with my calculator, so I'm going to go ahead and get rid of that and go full screen here. So the first thing that I will do is I will simply multiply on both sides by the denominator so that I can get rid of my fraction. The next thing I'll do is I'll go ahead and distribute that r. After I distribute the r, then I can start substituting some of my rectangular equations. So we know that r squared is equal to x squared plus y squared. And so r, just a plain old r, is equal to the square root of x squared plus y squared. We have minus r sine theta is the same thing as y, so that was a substitution, and then 4 just got carried down. All right, so then the next thing that I'm going to do is I'm going to take that negative y over to the right-hand side by adding. And then I will square both sides so that I can get rid of my square root. So on the left side, I got rid of my square root. On the right side, I'm foiling. So make sure you don't forget to FOIL. And then I'm going to start combining like terms. So I notice that my y squareds are going to zero each other out. My 16 I moved to the left side. My 8y I left over on the right side. Then I will divide on both sides. Well, here I actually just traded the two sides. And then I'll divide on both sides by 8. And then I can reduce each one of my fractions so that I have y equals 1/8 times x squared minus 2. So at this point now, I've taken my polar equation, the one with r's and thetas, and I have written it as a rectangular equation. And not only that, I have simplified it as far as it will go. And we are asked to graph here. Now, which would you rather do? Would you rather graph this one, or would you rather graph this one? And we're not told, so quite frankly, it doesn't matter. But just as a review, when I see this right here, this is nothing more than a parabola. In fact, we would have learned how to graph these even in previous classes, as well as in our very first chapter in this class. So when I see this, my brain just says, oh, well, this is a parabola that's shifted down 2 units, and it has a vertical compression of 1/8. So if it's shifted down 2 units, it's here. A vertical compression of 1/8 tells me that I'm going to be going over to the right 4 before I can go up 2. I'm not really doing a whole lot of explanation with that, folks. Like I said, that is a prior class. That's not even Math 111. And then that gives me my width for my parabola. Of course, you could have graphed that parabola in your calculator. You could have done polar mode and done it this way, or you could have gone back to your function mode in your calculator and you could have graphed this one down here. Either way, you're going to get the exact same parabola. I have included a sheet here that just kind of gives you some of the different things that you can graph on your calculator, so you can kind of play with these a little bit. But these are all the different types of graphs that you may see. You may also notice that I skipped a couple of examples. Those types of examples will not show up on your test, so that was why I chose to go ahead and skip those. All right, that's it for section 8.7.